So welcome to the third lecture on the mathematical structures course offered under NITheCS. In this lecture, we will be looking at mathematical structures which do not really have a separate name, but they bring together various other structures, so it's useful to consider them separately. We can nevertheless call them by the most obvious name, which is relations. So intuitively, a relation is some rule according to which we relate things. For example, this could be the family relation rule, where you are related to your uncle, for instance. In order to have a relation, we first need to specify the set of those objects that will be relating with each other. So in this case, this set would be the set of human beings. We call the set X. And it might actually be possible that we are relating objects between two different sets. For instance, if it's not the uncle relation, but rather the relation that relates every human being with the favorite food of that person, which could be a pizza, right? Then we have a second set, the set of those things that get related to, and then relation runs across these two sets. It is customary to denote it in a similar way as functions. We write an arrow and we label that arrow with R, where R is the relation itself. And mathematically, we can think of this as a subset of the Cartesian product of X and Y. So this would be the set of all related pairs. So in the first example, we could have X and Y being the sets of human beings. And then we include an ordered pair of human beings in that set R, if and only if Y is an uncle of X. Just a reminder that this symbol here means if and only if. So that means, of course, if this is true, then the other one has to be true. And if the other one is true also, then the first one has to be true as well. So in other words, we're saying that this is being expressed in this mathematical way. So then the set R will be the set of all possible ordered pairs where Y is an uncle of X. And in the second example, we have X is the set of human beings, and Y is the set of food types, and the relation is defined as follows. So the ordered pair XY belongs to the set when Y is the favorite food type of X. And as you can understand, this notion of a relation is a very general notion. It has extremely large amount of examples, both from real life and from mathematics. And here maybe we give one more example from mathematics. we could have x and y being the set of real numbers, and then we could have our relation to be the set of those ordered pairs such that x is less or equal to y. That, of course, means that an ordered pair belongs to R exactly when x is less or equal to y. And then we basically think of this relation R as the relation of being less or equal, right? In fact, we even have notation for general relations. We will write xry to imitate this kind of notation where the relation is inserted between the objects that are related to indicate that the ordered pair xy belongs to R. Okay, so we usually do not think of relations as structures. We usually think of relations as things that relate structures. One of the typical examples of relations in this way of relating structures is, of course, given by functions. In fact, let me add one more example here, where we have the same story here. X and y are both real numbers, and now the set R is a set of ordered pairs x, y, such that y equals x squared. And then we usually like to draw the graph of such a relation. And if we think of the graph, in terms of its set of points, every point has both x and y coordinate, right? And so we can actually think of the graph itself being the set R. But of course, not only functions have graphs. We could have something that's not quite a function. For instance, the set of those ordered pairs x, y of real numbers, such that x squared plus y squared equals 1. And then this thing will still have a graph. But now the graph will not be any more functional, in the sense that the graph will not be a function. The graph will be instead a circle, which is not a function because it violates the vertical rule test, right? So for each value of x, you could have multiple values of y. Or for some values of x, you have no value of y at all. So as such, relations usually model processes. For example, if we think of the x coordinate as time and y coordinate as distance, then you can have a motion being described by a graph such as the one that's shown here. But we now want to, in this lecture, we want to think of a relation itself as a structure. So a relation as a mathematical structure is a triple consisting of x, y, and R, where x and y are sets, and R is a subset of x cross y. It is worth noting that R does not determine x and y, right? If we go back to the circle example, here x could have been the entire x-axis, or it could have been a portion, as long as the circle situated, the x-axis projection of the circle is within that portion, right? At school and in the first year of mathematics, one usually talks about, at university, one usually talks about domain of the function, which is actually quite an ambiguous idea, because when we're given a function, which is a special case of relation, it doesn't necessarily determine what its domain or codomain are. So these things are in fact called domain and codomain of the relation. This would be called domain, and that would be called codomain. It's basically up to you to decide on which domain you want to consider your sets to be a function. But Of course, when the relation is indeed a function, then because the function needs to be defined on all points of its domain, then that domain does end up being unique for a given function. So there is a way to interpret the question of domain correctly. But still, the codomain is not unique, because there is no requirement on the codomain that necessarily everything in the codomain should be exhausted by the relation. So if I was looking at this one here, then from this graph, the domain would be forced to be entire x-axis, but the codomain could have been just the non-negative real numbers, or maybe all of the real numbers, and we wouldn't be able to tell just from the graph which one did we choose to play the role of y. Okay, so but for general relations, not just y but also x cannot be recovered from R. So that's why, as a mathematical structure, we do want to keep all three ingredients, x, y, and R, which have been chosen by us, in such a way that R is a subset of x cross y. If you have any questions so far, please ask. Otherwise, I'm going to continue on with describing some standard types of relations. So let's call this an atlas of relation types. Okay, first maybe let's actually fix terminology. So when we are given a triple like this, we don't call only the R part the relation, we call the whole thing a relation. And then we call this specific part of the relation its domain. We call this one its codomain. And we call this part its graph. Just like here, where the graph is the set of ordered pairs. So in this atlas, we're going to have general relations. That's when all the relations are considered together. And then we distinguish between a special type of such relations, which is when domain and codomain match. So this is the special type of relations where domain equals codomain. There is another type of relations when domain does not have to equal codomain, and among them are functions. And there is a very interesting property that generalizes being a function, and these are called difunctional relations. Difunctional relations. We're going to define what all of these things are in a moment. So functions are special kinds of difunctional relations, and there's special kinds of relations, of course. We can erase this line here. It passes via difunctional relations. Now, among the relations where domain equals codomain, there are various properties one identifies there. One of them is reflexive relations. And then we have transitive relations. And maybe at this point, it's useful to now start writing out what these things mean. So I think it's clear what domain equals codomain means. This just means that X part of the relation equals to the Y part. Difunctional relations are relations that have the following interesting geometric property, that if X is related to Y and X prime is also related to Y, and at the same time X prime happens to be related to Y prime, then, so this symbol here means then X is related to Y prime. We will come back to this and talk a little bit more about that. Let's leave it like that for now. What about functions? Well, functions are defined by the property that for every X in the domain, there is unique Y in the codomain such that the pair XY is in R, in other words, such that X is related to Y by the relation R. What are reflexive relations? These are relations where for every X in the domain, X is always related to X. And let me remind you that this symbol here means for every. What about transitive relations? This is when we in fact already encountered reflexive and transitive relations when we were discussing joint semilattices the other lecture. So these are relations that satisfy the following property. If that is true and this is true, then that must be true. But I would actually want to write both of these in this vertical way I wrote difunctionality. So let me do that. Sorry about that. I forgot about that. I wanted to write them in that way. So the reflexive relations are where we can always conclude that X is related to X. So once again, this horizontal line refers to then. And transitive relations are when from X being related to Y and Y being related to Z, we can conclude that X is related to Z. Now, if a relation is both reflexive and transitive, then it's called a preorder. Interestingly, there are two kinds of preorders. Called, so preorders satisfying the antisymmetry property and preorders satisfying the symmetry property, which are kind of opposite properties to each other. So preorders satisfying the antisymmetry property, they're called total orders. Sorry, they're not called total orders yet. Total order is something still different. They are called orders, or sometimes they're also called partial orders. So let me actually keep with more standard terminology. So we'll have here partial orders. And on the other side, we've got equivalence relations. So what are these? Partial orders are preorders, in other words, something that's both reflexive and transitive. And in addition, it satisfies the property that if X is related to Y and Y is related back to X, then X and Y must equal each other. Whereas equivalence relations are kind of opposite to that. They say that if X is related to Y, then Y must be related to X. And why is that opposite? Because imagine if I have something that's an equivalence relation as well as partial order. Well, then every time I have X related with Y, I will have Y related with X by it being an equivalence relation. But then by invoking the partial order property, I will get that these X and Y are equal. So every time x is related to something, x must be equal to that thing. So it kind of trivializes the relation. So the overlap of these two, in fact, as we just remarked, will be those relations which relate things with themselves. And remember that an equivalence relation still needs to be reflexive. So everything will have to be related to themselves. But then the only other things they can be related to are themselves as well. So we just get the equality relations. Equality relations. So these are just triples. This is basically relations where R equals the set of order pairs XX. Remember, we're now working under the branch where the domain and the codomain are the same. So I don't have to write Y there because it's the same as X. Okay, so we get this nice picture on the left side of important types of relations. There is another picture on the right side, but before I move to the right side, let me remind you that what the names of these properties are. So this thing is called symmetry, sorry, reflexivity. This thing here is called transitivity. This thing here is called antisymmetry. This thing here is called symmetry. Okay. On this side, we've got two types of functions. The injective functions, in other words, injections, and the surjections. What are injections? Injections are relations that are functions, so they have to have this property here. And in addition to that, they also need to have the property that if two different things are related to the same thing, if x and x prime are both related to the same thing, in other words, by the function they're mapped to the same thing, recall here that this unique y is then usually written as the value of my function at x. That's how I think of an ordinary function as a relation, in case it wasn't clear before. So an ordinary function is a relation which relates x to the corresponding y value. So now we're saying here that if f of x is y and f of x prime is y, then x and x prime must be equal. So two different things can't be related to the same thing. So this implying that x is equal to x prime. That's the injective property, and the surjective property tells me that for every y in the codomain, there exists x in the domain such that x is related to y. So these are functions, right? So then it says, what it says on a function is that for every y value, there is x such that y is actually the function applied to x. And if we overlap these two, we get something called bijections. So another name for bijections is one-to-one correspondences. So bijection is the same as one-to-one correspondences. And so that's just the overlap of these two. And then, of course, the equality relation happens to be a bijection. So we have a line going that way. Moreover, we can prove a simple result that I think one can prove that if you have a bijection that's an equivalence relation, then it must be equality relation. And one can also prove that if you have a bijection that's a partial order, I'm doubting myself, so I have to check it together, and also exactly the equivalence relation. So basically, this is not just the overlap of these two, but then this one also becomes the overlap of those two, as well as these two. So let's try to establish that in a way that will be sure of the result.
Professor, if I can just ask, these you may have mentioned, and I might have missed it, these properties that you've been talking about, they pretty much all require that x and y from the same set, correct?
The left ones, yes. So
okay,
in the left wing, yes, but not in the right wing.
Okay.
A relation that is both an equivalence relation and a bijection must be the equality relation. So let's prove that. For a relation to be equality, so consider such a relation x, y, and r. Now, by reflexivity, which is part of being an equivalence relation, by reflexivity we get that this is true. For every x, this thing is true. Now we want to prove the opposite, that if something is related to something, they must be equal. So let x be related with r. And this is where we use maybe the bijection property. We already know x is related to x, right? And now x is related to r as well, so to y as well. So x is related to x is related to y as well. Already in a function, right? We can't have x being related to the two different things. So already just by this property, that for every x there must be unique y, we will get that those x and y must be same. And that proves that it's an equality relation. And in fact, you see, we didn't even use it. It's a bijection. We just used the fact that it's a function. So we can generalize our theorem. So this thing is the equality relation. We proved that things related by this relation are exactly those things which are equal to each other, because those things that are equal are related by reflexivity. And if something is related, then they are equal by this argument. And as you see, we just use its function. So let's update our theorem. A relation that is both an equivalence relation and a function must be the equality relation. And so this is now a more general result than what we had before, because if already these and that together give us only equality relation, then of course this and this together will also give us the equality relation. One just needs to confirm that equality relation indeed is a bijection, but that's kind of obvious to clarify, to verify that the relation where things are only related to themselves will satisfy all of these conditions we stated here. Like, for example, here, if things are all related to themselves, then x will be related to x, x prime will be related to x, but that means that they're the same, and so they're the same. So the requirement trivially holds. So we've now intersected equivalence relations with functions, and now let's do the same thing with, you know what, maybe we can even be as brave as go to preorders, then we don't have to check for partial orders separately. And indeed we can, right? Because we only used, I mean, out of the properties of equivalence relation, we only used the fact that it's reflexive, right? We only needed reflexive and functional properties. So already reflexive relations that are functions are just the equality relation. We must be careful. It's not quite true what I'm saying, because we, no, it is true, isn't it? Yeah, it is true. I'm just checking that we didn't need to use symmetry here. So let's maybe go through this argument one more time carefully. So by reflexivity, we have this, and conversely, if two things are related, then we know we do have this by reflexivity. So then those two things must be the same. Yeah, so that proves what we want. So we can update our theorem further, where we say that a relation that is both a reflexive relation and the function must be the equality relation. So already these two things, when they overlap, they give us a unique possible relation, which is the equality relation. But of course, we have one equality relation for every set, right? That's why we have plural here. Otherwise, once we fix a set, there is only one relation, that's the equality relation. Now, the reason why I wanted to kind of show you this theorem is to show you that these two wings, this wing and the other one, they're kind of very far from each other. They don't like each other too much. The only thing that's in the overlap is sorry, I got interrupted because I read the comment by chat. Can we not prove that a bijection and a preorder give us equality? So yeah, so I think you might have written this before I realized it myself. So thanks for that remark, chat.
So Prof, that's actually Carlisle. He got in using my link, but as a consequence, he's also got my name. So there's two chats in the chat.
Okay, great.
But Carlisle's mark isn't. But Carlisle's mark isn't working. So if it's chat in the chat, it's Carlisle. If it's chat on the mark, then it's me.
Okay, got it. Yeah, I was surprised that you wrote it in chat and you didn't. Okay, great. Thanks, Carlisle. So yeah, so we did it slightly even better than that. We combined reflexivity and function to give equality. So that was as I said, to show you that these two wings are quite far from each other. They're kind of extreme opposites to each other in some sense. However, there is an interesting link on this side. You can have relations that are functions and transitive relations at the same time. Moreover, it turns out that when your relation is reflexive, transitivity is equivalent to being difunctional. Now, we did say that when the relation is reflexive, then function reduces to triviality, right? So when the relation is reflexive, things maybe are not so interesting, but nevertheless, I think it's interesting to observe that something that's a generalization of being a function, along together with reflexivity, becomes transitivity. So in a sense, you could think of like this being kind of matching with that one. But then, of course, if we do this transportation, then functions end up being just these ones, because that was done under reflexivity, which we know forces equality relation. But let's clarify these links. So let's see why is it true that for reflexive a relation that's reflexive, then it will be difunctional if and only if it's transitive. Maybe first we want to check why is every function difunctional. So that's actually not difficult to see. So to see that a function is difunctional, we look at this table here. We've got x is related with y, right? Now x prime is related both with y and y prime. But remember, under a function, there's only one y value. So this will force y and y prime to be equal, right? But if they're equal, that's good news, because it means that I can replace this y prime with a y. And I already know that x is related to y, right? So one more time, if this is a function, then because x prime is related to two different y's, those y's will be the same. So they will both equal to each other. And so y prime will equal y, and I can write y there. And then I have to prove this, but this was already a requirement in the first line. So I do get this because I've got that. And so that's how functions are difunctional relations. There was another question here by Carla. Are difunctional relations essentially relations that partition the codomain? Now that's a very good thought. Indeed. That's a very, very good thought. You can turn a difunctional relation into a function by that partition that you're pointing out, Carlyle, and maybe it's worth discussing that right now. So what Carlyle is saying is basically the following, and I'm going to illustrate what he's saying on an example of a difunctional relation. So let's try to build an example of a difunctional relation. So remember, for a difunctional relation, we don't need to work with the same set. We can have two different sets. Let's say this is set X, and this is set Y. And now let's identify some elements of this set X. 1, 2, 3, 4, 5 elements maybe. And maybe we'll want 6 of them. And let's have 4 elements on this side. Maybe 5. Okay, so I'm going to draw an arrow like this to indicate that X and Y are related. So when I draw a yellow arrow like that, it means that X is related to Y. Let's say X is related to Y, and let's say this thing is related to Y as well. And let's say that same thing is related to a different Y. Now I want to convince you that this will force X also to be related to that different Y by difunctionality. So why is that? I'm going to set up a scheme like I did before. So let's call this thing X prime. Let's call this thing Y prime. Now, the important part about this scheme here is that you've got a scheme where these two variables match and those two match. So they need to match in a shifted way like that. And then you're concluding from that a pair obtained by the leftovers, they are related as well. So just remember this picture, that we need to set up a scheme where those two match, and then the ones that are left over, they're the ones that are supposed to be related. Okay. So we'll now set up such a scheme for this situation here. So I've got because I want to prove that X is related to Y prime, I will make X and Y prime be the leftovers, right? And now I've got X related to Y, and then X prime related to Y, and then X prime related to Y prime as well by the yellow arrows. In fact, it matches, even by naming of variables, it matches with the condition we had before. So we had this scheme again. So those two and the leftovers should be related. So therefore, X will have to be related to Y prime, and that's the yellow arrow I drew. But now, because there is basically, I mean, another way of thinking about this is through zigzag. So there's basically a zigzag of this kind. So you see, these ones being the same and those ones being the same, it creates the zigzag where X is related to something, that to that, and that to the other thing, and then you want that zigzag to have the other diagonal also being a related pair. So with this geometric intuition, we could figure out that if there was a further zigzag, so there's already this zigzag here, right? But imagine there was a further zigzag where, let's say, this goes there, and that one also goes there. Now I can chase this zigzag from the start to the bottom the following way. So I first take that zigzag right there, right? And then I complete the diagonal with the yellow dashed arrow that I've already done. And then this gives me a new zigzag, which is this one. So that should give me another diagonal thing. So I eventually get that this also is related to that. So basically, this condition tells you that whenever you have a zigzag, you can jump from the starting point of your zigzag till the ending point, and that will also be a related pair. So that's one way of thinking about difunctionality. So let's insert these yellow arrows, and we can maybe have another disjoint zigzag going on here. Which will force, I'm worried now the picture's getting a bit complicated. So what zigzag do we have here? So we've got that matching, we've got these two matching, and those two. So that must create something there, right? That will create something there. And then the picture is too complicated to continue working on this picture. So let me actually take some of the arrows off. Maybe we just keep it this way, and now the point we want to make here, illustrating what Carl said, is that those x's that were involved as stepping stones for creation of the zigzag, right? They have corresponding things there, right? And this x, each of these, right? Each of these would have an arrow going to all the y's, because that's how we got these dashed arrows, right? Step by step. So if now I take all the y's which were involved in the zigzag and put them in one group, like that. So this is the group I've created now, out of those y's that were involved in the zigzag. And if for a moment I imagine that I stick all these y's together, then we will no longer have a scenario that the same x relates to two different y values, and so we'll get a function out of it. So that's the link between, so the partition that Caroline was referring to is something useful. So the partition we get on this, on the set y, by putting all the y values in the same group once they come from a certain zigzag, certain common zigzag, that partition is useful because that partition allows us to replace this set with another one, so that our relation now going into that other set becomes a function. So that's one link between difunctional relations and functions. We could formalize this and prove this rigorously, but I don't really want to go in that direction right now. So we've looked at, okay, just to complete this example, how do we know that the thing we obtained is indeed a difunctional relation? Well, it's not yet. We still need to complete more zigzags, right? So everything that was departing somewhere must be departing to all the y values because of this zigzag situation. So we've taken care of that. This is true for that x value. It goes to all the y values, but we also need to take care for the other ones. Like, for example, for this one, how do we know? We already know we've got arrows there, but how do we know we've got an arrow there? Well, we've got an arrow there because there is this zigzag, this one, that one, and that one. If you think about it, if you look at this zigzag, right, that will produce its own diagonal arrow this way. So that will ensure that also x prime is connected to that. And then the same for this. How can we get an arrow going from here all the way across there? By a zigzag, which goes this way, and then that way. And so that will ensure an arrow going there. Of course, you have to iterate the definition of difunctionality. You have to apply it several times before you get all these arrows that are forced to be there. And now we get a full example of a difunctional relation. So this relation will be difunctional by the geometric idea that all zigzags are complete. Okay. Now going back here, we remarked that functions are difunctional relations. We also looked at an example of a difunctional relation, which is not a function, right? This cannot be a function because a single x value gets related to two different y values. But now let me go back to that observation that for reflexive relations, transitive and difunctional relations are the same. And in fact, for reflexive relations, not just transitive and difunctional, also symmetric relations are the same as transitive and difunctional ones. Sorry, what I want to say is that for a reflexive relation, every difunctional relation is both transitive and symmetric. And so it becomes an equivalence relation. So equivalence relations are examples of difunctional relations. And so we have another line there connecting these worlds. Remember that equivalence relation together with being functions, that's a completely dead end because we then just get equality relations. But it turns out equivalence relations can be, you do have the property of being difunctional. And moreover, these properties overlap of being reflexive and being difunctional, which is what we're going to prove now. I think previously I was saying that for reflexive relations, difunctionality is the same as transitivity. I was actually making a mistake. I didn't intend to say that. What I wanted to say is that for reflexive relations, being difunctional is the same as being transitive and symmetric at the same time. Sorry about that. So let's prove that theorem. A reflexive relation is difunctional if and only if it is an equivalence relation. So let's begin with a reflexive relation that's difunctional, and let's try to prove that it's an equivalence relation. So to prove it's an equivalence relation, we need to establish transitivity. So we need to get the scheme that x related to y and y related to z should give us x related to z. The question is how to achieve this. Under which assumption we want to achieve this? So reflexive. So we can just write out the reflexivity property as such a scheme as well. So this is the reflexivity property. Difunctionality, if you recall, is this zigzag property, x r y, x prime r y, x prime r y prime, and then we have x r y prime. And so these two properties together, on the left side, should allow me to conclude the right-hand side property. So let's write this down so that we're now saying that these two things together can be used to prove that one. So in other words, we've got an implication this way. And then we will want to prove also backwards that this and difunctionality, sorry, this and transitivity together with reflexive symmetry gives back difunctionality. So we want actually not just transitivity, but we also want symmetry, right? We said that equivalence relations is what we get if we take the functional reflexive relation. So let's write down for symmetry as well the corresponding table, x r y, y r x. There we go. And now let's try to discover this proof together. So I know that this is true. I know that this thing is true, and I want to prove that property and that property. How? How can I achieve that? Any suggestions? So these are the two properties we can use, and these are the properties we want to prove. Let me give you a hint. The trick is to use those zigzags we talked about. You want to yeah.
Sorry, Prof. For I don't know if this assumption would restrict us, but to start with trying to prove transitivity, could we assume that x prime is y? Or no? Yeah.
You want to take x prime to be y. Why not? Let's try. Let's see what happens, right? So let's apply this rule, the rule of difunctionality, in the case when x prime is y. Shall we? Then we get x r y, y r y, y r y. Sorry, y r y prime gives us x r y prime. Okay. Does this give us the transitivity?
If we refer to y prime as the equivalent of z.
Okay, let's replace y prime with z. Good idea, yeah. Do we then get transitivity? Remember, for transitivity, we want to get this third line from these two lines. Here we have an extra middle line. So if I start with these two lines, from these two lines, I need to get that one, right, as a conclusion. Sorry about that. So, but don't forget that we have reflexivity as well as an assumption, huh? So if x is
yeah, so kind of like the second line we kind of already knew, meaning on the left, the y relates to y.
Exactly. If we start with this, we can always add y r y here because we have reflexivity, right? So thanks to reflexivity, we can conclude our y r y from that, right? In fact, for that, we don't even need any assumptions. We can always say that something is related to itself. That's what reflexivity is. But once we've got these three, then, as we know from these three, we can conclude what we want. So we're done. Do you agree with that, Chad?
Yeah.
Fantastic. And so basically, we've been able to kind of, what you saw, the pattern you saw there is kind of to expand this into this form, into the zigzag form, to then get the desired result. Now, can we expand? Can we do the same thing here so we can get symmetry? So how do we expand that one in a zigzag form to get what we want?
Can we not say that since we have a relation, since we have a relation from since we have a relation from x to z and x to y and y to y, since y is related to z.
Just a moment. We don't worry about z anymore, right?
I'm trying to.
Symmetry.
I suppose I was trying to use z as some sort of stepping stone to turn the relation around.
Mm-hmm. Well, the question again boils down to what substitutions to use, basically, right? If we can get away with just one set of substitution.
Yeah, in the chat, I think Carlisle said pretty much what I was suggesting.
Right, fantastic. So we add, so if we have that, we know that we can, by reflexivity, we can add these. And then it's just a matter of rewriting them in the order that to fit the zigzag. So that would be that would be this order. So here we have the matching pair, and then the leftovers will be matched. And so I've just rearranged the order to check that that functionality works, right? So this is just that one is just that, and that one is just that. And so then we can indeed conclude that y is related to x by that functionality. Okay, fantastic. So we've got that being reflexive and difunctional implies being symmetric and transitive, and hence an equivalence relation. So we proved this part. This implication. Now let's prove backwards. No, sorry, actually not backwards, because we want backwards together with reflexivity. So now we are going to put these two along with reflexivity together, and we will try to prove that these three properties give us difunctionality. So we want to get from there that x ry, x prime ry, and x prime ry prime. From this we can conclude x ry prime. So let's maybe begin with the three lines: x ry, x prime ry, x prime ry prime, and let's see where we can proceed, how we can proceed by employing transitivity and symmetry. What can we conclude from here using, well, reflexivity as well, right? Geometric way of thinking about this helps. This is the situation we've got. So this, my first arrow is the first line, second arrow is the second line, and the third arrow is the third line. And this is the zigzag we want to complete. But now we know that the relation is symmetric and transitive. So I think it should be obvious from this picture how we use symmetry and transitivity. We want to get from here to there. So there is a one-way road from town X to town Y. There is a one-way road from town X prime to town Y. There is a one-way road from town X prime to town Y prime. And now you discover that all of these one-way roads are actually two-way roads because of symmetry. Then can you get from town X to town Y prime? And if you can, then how? Remember, transitivity is this intuitive idea that if you take one-way road in one direction and you take follow-up one-way road in the other after that, then you can get across. That's what transitivity is. And symmetry.
Prof. Carlisle, sorry, Carlisle has a suggestion in the chat.
Yes.
Sorry for interrupting.
So no problem at all. So we reverse this arrow. That's quite obvious, right? So this is how we go. Yeah. If it's possible to reverse this one-way road, then we just go this way. We take this direction, then there, then there. So what am I trying to say? exactly what Carlyle wrote there. So we're first going to use symmetry to reverse the middle, this one. So we'll have y r x prime, and then we use transitivity twice. So once we have this reverse direction, we can then combine these two into one, and then those two into one by using transitivity twice. Okay, so what does that mean? So xry, yrx prime, that together gives xrx prime, and now we have xrx prime and x prime ry prime, so that together gives xry prime. I hope I'm not too fast. If I am, please do stop me and ask me to repeat some of these explanations. Okay, so this then is basically a sketch of the proof. I say it's a sketch because we just brought the pictures. We didn't write all the words and everything, but I think it's clear how the sketch can be completed. So it's an interesting link we established, that reflexive and difunctional relations give us precisely the equivalence relations. And so this is what we have, the atlas of different types of relations. Now, relations that are of this kind, they're usually used to build structures. For example, a joint semilattice that we talked about last time. Every joint semilattice, as we saw, is a special type of set equipped with a partial order. We described how we can get partial order in a joint semilattice. In fact, I think we even defined a joint semilattice as a partially ordered set having joints. So these things are kind of structure building properties. In fact, I should be more precise here. More these ones are structure building properties. This one is used to for things like quotient structures, which, if you know what that means, then you would know its significance. So these are things to so if these are things that are used to define structures, then the equivalence relations are used to build new structures out of given ones. Whereas these things here are used for describing links between structures, like, for example, a linear map between vector spaces is a special kind of a function. The difunctional relations do have some uses, but they're not so significant as the rest, as these ones are. And there are many other types of relations one can introduce and that people study and so on. So one can actually grow this atlas and then include more details. I've just shown you some of the key ones, and also I really like difunctional relations because they can be seen as almost like equivalence relations without this requirement of domain and codomain being equal to each other. In other words, take equivalence relations, try to get out of this requirement. You can't really, because transitivity, you see, is defined in such a way that you need the y to be in the codomain and in the domain at the same time. So to state transitivity, you kind of need this property. So now the question is, can we still state some kind of equivalence relation property without the domain and codomain being equal to each other? And in some sense, the result we proved shows how to do that, that you can turn equivalence relations into difunctional relations when you remove this property. We're now going to prove something interesting that links up these things, and specifically the difunctional relations, with a bit of algebra. I think I can assume. Okay, let me first ask. So, does everybody know what? Okay, let me actually be very concrete, so I don't have to step into a territory that you might not be aware. So let's do something of the following kind. Let's take. So this is just for fun. Let's take the integers. Okay. The integers form a monoid, right? Moreover, this monoid is in fact a group because every element has an inverse. So we consider this monoid where addition is the usual sum, and then we note that for every element x, we have another element which is called minus x, such that this sum is 0. And of course, by commutativity of addition, we also have the other way around. Okay. Now we could take the Cartesian product of integers with itself. This will still be a monoid. We can define operations just coordinate-wise. This is how, for example, we can turn a real line into a plane, and the structure of the real line transports to a plane, and that's what gives rise to the two-dimensional vector space. So how do we define the addition and the 0 in the Cartesian product? Well, the pair AB plus the pair CD equals A plus C, B plus D. And the 0 can be defined, so the 0 element of this monoid is the element with each coordinate being 0. And we also have minuses there because we could take AB plus minus A minus B. And of course, by the way we defined addition, this will be A plus minus A, B plus minus B. And that, of course, will be 0, 0, which is our 0. And addition is commutative, so we also have that equals minus A minus B plus AB. So I don't remember if we defined what a group was in the first lecture. We did certainly define what a monoid was, but this monoid together with that gives us a group. And this shows that we have another group here, Z cross Z. And now let's take a relation on Z, which happens to be, in addition to just being a subset of Z cross Z, because that's what a relation is, it's a subset of the Cartesian product. Let's require that this R is a subgroup. What does that mean? It means that it's closed under the operations. So it means that if pair AB and pair CD are related, let's actually write in terms of our previous scheme. So if A is related to B and C is related to D, now think of these as ordered pairs, then we want the sum of those ordered pairs to be still in the relation, but that sum is obtained by adding them coordinate-wise, so that will be A plus C is related to B plus D. So being a subgroup means that it's closed on the operation of addition. And we also want it to be closed under the inverses. So if A is related to B, we do want minus A to be related to minus B. So let's consider relations having these two properties. So relations on integers having these two properties, which conceptually say that the relation is a subgroup of the Cartesian product of the group of integers with itself. It turns out, quite remarkably, that every such relation is going to be difunctional. And let's see if we can figure out why. I did forget to maybe mention one more property, which we might be able to derive it or not. I'm not quite sure right now. Actually, we will be able to derive it, so we don't have to worry about it. Sorry. So let's prove that this relation is difunctional, the one that has these two properties. So let's see if we can get the zigzag story going in here. So let's take r x r y, x prime r y, x prime r y prime. Let's see what we can do with these pairs using these two rules to eventually derive that x is related to y prime. Any ideas? Maybe let me give you a little bit of a hint. What these rules basically tell us is that I can perform same kinds of manipulations in the coordinates. I will still get related pairs. So I can add them, and I can take minuses. Therefore, I can also subtract them. And now let's focus on these two columns. What kind of operation should I perform? But they have to be the same operation in both cases, so that it spits out x on the left side and y prime on the right side. So somehow I want to present x as some kind of polynomial, but now what I mean by polynomial is polynomial with integer coefficients, of course. Polynomial of x, x prime, and x prime. And at the same time, I want to present, so this will be my x, and I want to present the same y prime, I mean, not the same, but the y prime, I want to present it as also a polynomial of the same kind, but now with variables being substituted, y, y prime. Can you think of some algebraic expression of three variables? Abstractly, let's think of these variables as u, v, w. What can we do with u, v, w so that when we apply it to x prime, we get x? But when we apply it to y prime, we get y prime.
Well, in the first case, we could have x equal to x plus x prime minus x prime.
But then we will end up with minus y prime, and we want y prime. So maybe you can change that a little bit. You said x plus x prime and minus x prime.
X minus x prime minus y x prime.
There we go. Well done, Chad. So if we do this, and we do the same thing in the second line, we get y minus y plus y prime. You see, we are doing the same thing in both cases. But it does give what we want, right? So now let's do this more step by step. So we first want to get minus x prime y, minus y, sorry. So we'll take this middle row and apply it to this, to that we will apply this rule. So we'll have minus x prime r minus y. And then we will apply this rule to this row and that row. What are we going to get? We're going to get x plus minus x prime r y plus y. Okay, and then we apply not plus, sorry, minus, plus minus y, right? And then we apply the same addition rule, but now we're going to add this thing we got with the third row. That was the one we hadn't used yet. and then we will get x plus minus x prime plus x prime are y plus minus y plus y prime. And of course, this is nothing other than, because it just simplifies to, here it simplifies to x, and there it simplifies to y prime, which is exactly what we wanted for the functionality. Recall that the functionality wanted to have these leftover ones being related, which is what we have here. So it's this curious phenomenon that all relations on integers, right, that happen to be compatible with the integer operations, the addition and the minusing, such relations are actually called compatible relations. And when such relations are equivalence relations, they're called congruences, and this leads to congruence theory on integers and so on, but I'm not going to go into that right now. They all happen to be difunctional. So, and this actually is a feature of groups, because you see this combination we expressed here had nothing to do with integers. We could do this for arbitrary groups. So the groups have this feature that when you require that those relations on groups to be compatible with the group operations, to be compatible with the group structure, basically, it turns out that all, not just that there are some specific relations that are difunctional, but all of the ones become difunctional, right? And so you can have various different properties of relations, and then for certain mathematical structures, you discover that when relations are compatible with that structure, all relations turn out to have that property. And in fact, this kind of enters into one of my research interests. I have some joint work with two collaborators where we explore these kinds of properties of relations being compatible with structures at the more general level of category theory. But coming back here, the fact that compatible relations on integers turn out to be difunctional, together with this fact that every reflexive relation is difunctional, will have an important consequence on describing congruences for groups. But I need to refrain going there, because that will be a topic for a separate lecture. I just wanted to tell you that even though we said this is for fun, it still is an applicable result, and specifically one of the applications is in developing theory of congruences for groups and also other algebraic structures. Okay, but congruences is something we definitely need to look at some point, not in this lecture though. There will be special type. Basically, in general, congruences are equivalence relations that are compatible with your mathematical structure, and they allow you to quotient out your structures, just like ordinary equivalence relations allow you to quotient out sets. And maybe that's something what we want to talk a little bit now. So let's see how. Let's look at an application of equivalence relations in terms of quotient sets. And maybe I shouldn't do this separately, because there is already a lecture on this that was given in the mini school for elementary introduction to set theory. I will post a link to that mini school, and you can have a look at that last lecture there, where Dr. Goswami and I, we discussed importance of equivalence relations and how you can use to build other sets from given sets and so on. So I'll leave that material to that lecture. You can watch that if you are interested. Okay, so let's go back to our atlas. I'm just trying to think if I missed anything I wanted to mention in this context. Yes, I remember now what I wanted to say. So when we are working with relations as structures, we've got this classification of different kinds of relations, but we also want to, so relations have this double nature. They also serve as transportation from one set to another. I can think of a relation as transportation, and that has already been kind of become apparent through a picture like this, for example, which looks very much like describing a function, except that it's not a function, kind of a mapping from one set to another, right? So relations can be composed just like functions can be composed, and it's quite easy to compose relations. But then it turns out that the composite of relations is a useful language for describing properties of relations, which is what I want to dedicate the rest of this lecture to. So if I have two relations, x, y, r, and y, zs, I can multiply them. The product is called the composite of relations. It will be a relation. It's almost like with matrices. You can think of this as, of the relation R as being almost like X by Y matrix. Why can you think of it like that? Maybe first, I want to show you why you can think of it like that. So think of X in terms, let's say X is a finite set, right? And Y is a finite set as well. Then you set up this matrix with n columns, and you set up, and your rows are m many of them. So now you've got these spaces, these slots where you can insert things, right? So whenever x is related to y, the value of that entry in the coordinates xy, actually in the coordinates yx, because x represents column and y represents the row, right? I'm just confirming I want to set up it that way. Right. So you make that value equal 1. And whenever x is not related to y, you make the value equal 0. So 1 is for true and 0 for false. And so then you populate your matrix like that. So you've got here A11, A12, A1n, and this is just another way of encoding a relation, right? Because with 0 and 1, I can determine exactly when some x is related to y. So let's look at a specific example of this. So let's say I've got a matrix 0, 1, 0, 1, 1, 1, 1, 0, 0. So now I label my columns and rows 1, 2, 3, 1, 2. So this turns out to be a square matrix. I can now think of this as a relation from the set 1, 2, 3 to the set 1, 2, 3. How do I set up the relation? Well, to decide whether 1 is related to 1, I look at the entry at 1, 1. It's 1, so that's related. So I put an arrow like that. Now, 1 will be related to all these values there where I have entry 1. So actually, it's related to everything. Let's look at 2. Well, I see 2 is only related to 2. And 3 is related to 1 and 2. So that's how I can think of a binary matrix, basically as a relation from an n-element set to an m-element set. Okay, so just like matrices can be multiplied, also relations can be composed. And in fact, composition of relations will, when the sets are finite, will match with multiplication of binary matrices. And the way we can describe the composition is the following. So remember that when you multiply matrices, the dimensions are carried forward like this. So that will be your first dimension, and that will be your last dimension. So it will be x, z here. And then what we put here is called S composed with R, and is defined the following way. It is the set of those pairs xz such that it is possible to find a y that links them up. So x is linked to y with R relation, and y is linked to z with S relation. And of course, when okay, I'm not going to go into further detail now, but it might be already obvious to you why this links up with matrix multiplication, because you're basically going to be summing up over all possible values of y, but your sum needs to be such that when there are several ones, 1 plus 1 is basically 1. So you'll be working not in usual arithmetic, but in arithmetic where 1 plus 1 is equal to 1. So that summation is actually the logical join operation where we think of 1 as truth and 0 as false. But don't worry if you don't understand what I just said. So let's draw the 3 sets. We've got x, y, and z. And I'm now declaring that if I've got an x here and I've got a z here, if I want to figure out whether by the composite relation they're related, all I need to do is to find a y which links them. So if x is related to y by the R relation, remember this is the R relation, it goes from x to y, and this is the S relation that goes from y to z. If x is related to y by the R relation, I am kind of abusing the language a little bit. I'm referring to the entire relation and just its graph with the same letter. That's a common practice in mathematics with dealing with mathematical structures, not to overload the notation. So if x is linked with y and y is linked with z with the other relation, if I can find such passage, then they will be related by the composite relation. So existence of R relation here and S relations here is what ensures the existence of the composite relation there. And of course, if S and R are functions, then this is just the composition of functions. That's how we compose them, right? We map by one function, and then we map the result by the other function. So that's exactly the composition of functions. So this notion of composition of relations is actually the generalization of the idea of composition of functions. Now, this is one important construction you can perform on relations to compose them. And another one is to take the opposite relation, something we don't have for functions unless they're bijections. So if I've got a relation like that, I put a circle on the top there, and then it becomes a relation which has changed the direction. So now the codomain becomes domain and domain becomes codomain, and the graph swaps around. So R op is a set of all pairs yx such that the pair xy is in R. It is really, in terms of the picture, if my relation initially was the graph of the y equals x squared function, right? And then it would swap around along the y equals x axis, and the opposite relation would be this. So this is R. This would be R op. Okay. Now with these two operations, the operation of composing relations and the operation of taking the opposite of a relation, so let's maybe clarify this here. This is called the opposite relation. And this one is called composition of relations. I can express difunctionality as follows, and I'm going to prove this as a theorem. a relation R, and as I told you, as I warned you before, I'm using the same R to represent the graph and the entire relation. The relation R is difunctional. If and only if R composed with R opposite and composed with R is a subset. It actually, we can even say that it's equal to R. We can in brackets say which is equivalent to R composed with R opposite composed with R being equal, being a subset of R. So this property of difunctionality is nicely expressible in terms of these two operations as an algebraic identity. Okay, so let's see why. Let's describe the elements of this triple composite. So what is the triple composite in the first place? Well, it turns out that composition of relations is an associative operation. So let's draw a picture. So R was a relation from X to Y. Right? Now, our opposite will be a relation from Y to X. And then another R is a relation from X to Y. Now, in general, when you have a setup of relations this way, X, Y, Z, T, and you've got three relations, R, S, oops, I ran out of letters now. I call it Q, R, and S. It turns out that composite of S with R and that further composite with Q equals S composed with R composed with Q, just like with functions. In fact, the fact that composition of functions is associative is a consequence of the more general fact that composition of relations is associative. And I would like to leave this as an exercise for your own exploration. And so that's what this triple composite represents. Because it's associative, it doesn't matter how we put the brackets, so we just then don't put the brackets. Okay, so, but let's still compute what the triple composite is. So, maybe first we compute this composite, and then compose it further with R. So what is this composite? It's the set of ordered pairs X X prime such that no, I actually want to, sorry, I want to first compute, I want to arrange my expression this way. So it's R composed with set of ordered pairs X X prime such that there exists a Y such that X is R related with Y, and that is R op related with X prime. But remember, the R op relation is just swapped around version of R relation. So that's the same as to say that there exists a Y such that X is related to Y, and X prime is also related to Y. Okay. So what we seeing here is what is emerging here is our scheme. This one. And now composing it further with R will give us this situation. So composing with R indeed is what then? So remember how then X, so it will be pairs X, Y prime such that there exists an X prime such that X is this related to X prime. In other words, X is R composed with R related to X prime, and that X prime is R related to Y prime. And now I already know what this means, right? This has been expanded here. And so overall, I get this set of pairs X, Y prime such that there exists not just X prime, but also there exists a Y such that, so I'm just expanding this part inside the other one, such that X is R related with Y, and X prime is R related with Y, and this final bit, X prime is R related with Y prime. So we get exactly these three terms that we have in this scheme. I just want to complete some brackets here that I've missed. And also to remind you, if I haven't done so already, that this symbol here means there exists. Okay. We've computed that triple composite we had. And now we're going to analyze what it means for that triple composite to be a subset of R. So triple composite is this. Now if I say that this thing is a subset of R, that is saying that this set, right, is a subset of R. But what does that mean? It means that every element of the left-hand side set must be in the right-hand side. So saying that it's a subset of R means that is the same as saying that whenever X prime Y, XY prime is an element of R composed with R op composed with R, we have that the same XY prime is an element of R. Right? Okay, but we know what this simplifies to, right? Or maybe complexifies to. So in other words, whenever, I mean, this is equivalent to that. That's the result of our computation. So in other words, then we're saying whenever this is true, right? Whenever there exists such X and Y, we must have X, Y prime being in R. But that's exactly our scheme. That's exactly what our scheme was telling us, that whenever X and Y prime can be connected by a zigzag, in other words, whenever Y and X prime exist, such that these three conditions hold, then X must be related to Y prime. That's exactly what we're saying here, except that now we're just using these fancy symbols here to express the fact that X prime and Y must exist, which was already kind of assumed here. So this becomes directly equivalent to the property of difunctionality. So R is difunctional if and only if this triple composite is a subset of R. So that takes care of this part of the theorem which says that the thing was equivalent to that. Now, why is that thing equivalent to the triple composite being equal to R? Because it turns out that R is always a subset of that triple composite. For every relation, R will always be a subset of this triple composite, which we can now demonstrate.
Sorry, Prof. Did we at all ever state that X and Y are elements in R, or is that assumed considering the conditions we're working in?
So because all the variables we've been introducing here, they've been being controlled by R and by the relation R, and because the relation R only has those pairs related, which come from those sets, and that we don't have to worry about that issue.
Just to clarify the notation, if we had for some reason called the relation, I don't know, a big F, for example, where we say X or Y, would we have said X F Y?
Yeah.
Okay.
Exactly. So why does this always hold? Well, that's easy, because if I have X R Y, then I can write X R Y op R op X, right? Because if X is related to Y, then Y will be R op related to X R Y. So I get this thing that, I mean, those things exist that ensures that X and Y are in that relation. Remember, that's how that's how the relation was defined, right? So if you look at this part here, right? So this triple composite, well, actually not that one. If you look at this one, so we need to get the zigzag, and maybe I should describe this more explicitly. So that implies that, and furthermore, this gives me, if I revert back to the usual R, XRY and XRY and XRY. This is a special instance of our scheme, because remember, our scheme was to have these two the same and those two the same. So if I repeat XY in every row, then that is fulfilled. So that shows that XY will be in the triple composite relation. So X will be R composed with R op composed with R related with Y. So because this other inclusion always holds, then just having one inclusion is equivalent to having equality. So this thing is further equivalent to that being equal to R. And that's how we have proved now the theorem we wanted to prove. Now, we kind of went a long way here, because you might not have been used to composition of relations. Once one gets used to it, then one can actually confirm this theorem just by imagining the kind of patterns of related pairs you get by the composite, and get convinced that actually it is really difunctionality. And in a similar way, one can prove other similar theorems like that. So we have more theorems which we're not going to explicitly prove now, but the proof will be even a bit shorter than these ones. That, for example, that the relation is symmetric if and only if R is a subset of R op, which will further be equivalent to R being equal to R op, for a slightly different reason why subset and equality was equivalent in the previous case. It uses the fact that double op of a relation is the same relation back. And then also transitivity can be expressed in this way. That will be that R composed with R is a subset of R. And then one can develop this language a bit further and just use these ways of thinking about these properties and prove in a more algebraic way by relating these properties with each other, reprove the result we had before, that reflexive relation is difunctional if and only if it's an equivalence relation. So I just wanted to show you this kind of something that people sometimes call calculus of relations, where you try to express your properties of relations in terms of composition of relations. A little fun exercise for you for the evening. The question is, what happens if you take this relation here, the one we had here, this one. So let's take a relation where the radius of the circle is 1. Let's call this relation R. Compute R composed with R. I mean, it's a bit obvious that this relation will be symmetric, so R will be equal to its opposite. Compute R composed with R. Compute R composed with R composed with R 3 times, and so on. What will they be? And you will discover something quite interesting there. And then maybe if you note that this relation is actually symmetric, because circle is symmetric in a way, then we'll know this is the same thing. And then maybe you can compare this triple composite with R to establish whether a circle is a difunctional relation or not. We already said that circle is not a relation, right? Is it difunctional? You can also do the zigzag approach, of course, to determine that. But maybe after you have explicit computation for this triple composite, then you will be able to apply the theorem here to decide whether a circle is a difunctional relation. Fun question: is a circle a difunctional relation? All right, so I would like to once again come back to our atlas. So for the rest of this course, relations of these different kinds will feature quite a lot. Already with joint semilattices, we encountered partial orders, although I don't remember if we gave that name explicitly or not. Then these 2 different types of functions are very important. Maybe I can add one more result that would link composition with functions. So there is this beautiful theorem that says that any function f from x to y can be presented as a composite. Now, because a function is a special case of a relation, we can compose functions, and of course that will be the usual composition of functions we know. Can be presented as a composite f equals m composed with e, where e is a surjection and m is an injection. So remember, we said that kind of important classes of functions are injections and surjections, and now using this language of composition of relations, we figure out that any function actually decomposes into an injection and a surjection. So in a way, products of injections and surjections give you all possible functions, and that's why injections and surjections are important, actually. Now, moreover, in fact, this decomposition is unique in a suitable sense. It's not unique literally, but it's almost unique, and you might want to think about in what way it is unique as part of your original exercises for this lecture. I think this is where I need to stop. We've also reached the end of, at least we're very close now to the end of 2 hours. Let me stop here. If you have any questions that you would like to be still in the recording, you can ask them now. Otherwise, I'm going to stop the recording, and then we can have a further discussion if you would like to.